Today's video is entirely dedicated to the Robotarium, what it is, how it works, and how anyone around the world, including you, can use it for absolutely free for educational or academic purposes, like applying the methods and algorithms learned in this video series. Let's get started. Hello, my name is Sean Wilson, Director of the Robotarium Laboratory. Today we're going to go over the Robotarium, what it is, and how to interface with it. Together we'll cover how to create a user account, download the necessary software and APIs needed to interface with the Robotarium testbed, and create our first few experiments, which we will run in simulation and deploy on the Robotarium testbed. So what is a Robotarium? Robotorium? Robotarium? Good question, me. The Robotarium is a remote access multi-robot testbed here at the Georgia Institute of Technology. Its mission is to democratize access to robotics, meaning we let anyone around the world, absolutely free of charge, use our robotic hardware and our testbed to test out and validate their experimental algorithms. The reason we do this is a fewfold, but the primary reason is to reduce the barrier to entry to experimental robotics. Robots are expensive. It's quite expensive to buy the robots, get the tracking system up and running, buy the networking infrastructure, have a closed and secure room to keep all of your stuff in. And even if you have the resources to buy all of these things, you may not have the time needed to instantiate the testbed, get it up and running, debug all of the software and debug all of the hardware. And beyond that, even if you have the time to instantiate it, you may not have the resources and time to keep it going for long periods of time. So the Robotarium sidesteps all of these issues and provides a research quality testbed for anyone around the world to use without having to invest all of this time and money to get into the experimental robotics game. And now, with that brief understanding of what the Robotarium is, its mission, and what it's meant to do, let's start talking about how to actually interface with it and use it. The first step is to create a user account, so let's start there. To be able to submit experiments to run on the Robotarium, you will need to create a user account on the Robotarium website. Through this account, you will be able to communicate with and receive notifications from the Robotarium team, submit experiments to be run on the testbed, and access data from completed experiments. To start, open your favorite web browser and navigate to the Robotarium website, located at www.robotarium.godtech.edu. Once the page is loaded, click the Sign In button in the top right-hand corner of the web page. You can sign in with either Google or another email. For this video, I will choose the more generic Sign In with Email option. This page is how you would log in if you already had an account. But to create an account, let's select the middle option, Sign Up. Now, enter the email address you would like to receive experiment updates and communications from the Robotarium team through. Create a password and complete our CAPTCHA check. Next, update your profile information. The profile information is confidential and only used by the Robotarium team to keep track of user demographics. The required fields are indicated with the red stars. Finally, you'll have to verify your email via a link sent to the email address you created your user account with. Once you finish this step, you're done. You'll have to wait to submit experiments until your account is manually approved by the Robotarium team. Now that we have a user account, let's go over the development cycle of the Robotarium. How we take our ideas, our methods, our algorithms, and translate them to experiments that can run on the Robotarium and give us back validation that what we have an idea of actually works in the real world. Before exploring how to program an algorithm for the Robotarium or interface with its application program interface, let's briefly discuss the development cycle in order to successfully deploy a remote experiment onto the Robotarium and continuously improve them until the desired performance is achieved. The first step of this development cycle is to come up with an idea that you would like to see come to life with a single or collective of robots. This can be examples presented in this video series, a rigorous multi-agent optimization strategy, a single robot driving in a straight line, or any other idea that you can come up with. After establishing the foundation of your idea, it's time to translate your algorithm into a script for the Robotarium simulation API. This allows you to test your algorithm's performance locally on your computer, check for any errors, like robots colliding, leaving the testbed, or doing any other misbehaving, and visualize the expected behavior before submitting it to run on real robots. In the example simulation shown here, 20 robots are tasked with covering the interlocking GT logo. Once you are satisfied with your developed algorithm's performance in simulation, you can submit the script to the Robotarium website using the same account information we created previously. At this point, you're done. Your experiment is put into a first-come, first-served queue, and you will have to wait for your experiment to run. This can take as little as 10 minutes to as long as a day, depending on how many other users are submitting around the same time. When your experiment is pulled from the queue to run, it is first verified to make sure the script doesn't run forever, its syntax is correct, and that there are no errors with the submission that could damage the robots or other hardware on the testbed. If any errors are detected with your submission, you will receive an email alerting you of the problem, and details of the issue will be available through your user account on the Robotarium website. If the experiment clears verification, it is run on the Robotarium testbed. When your experiment is completed, you'll receive an email notification. Any data you save from your experiment is uploaded to your user account along with an overhead video of the experiment, like the one you see here. You can watch the video, analyze your data, and if you're happy, you're done. If there are improvements you would like to make, you can continue with the development cycle, modify your idea, make changes to your submitted script, and keep submitting until you get the performance you desire. Now that we've covered the Robotarium development cycle, let's go over how to download the necessary software to interface with the Robotarium. First, let's navigate to the Robotarium website at www.robotarium.gatech.edu. Next, click the Downloads button from the main page. This will bring you to a web page with links to the GitHub repositories hosting the software we need to download. Currently, the Robotarium has a MATLAB and Python development environment, but for this video series we will focus our development in MATLAB. If you are unfamiliar with MATLAB, a link to self-paced online training with no license requirements is in the description. Click the MATLAB link to navigate to the MATLAB repository. All the files necessary to run the MATLAB version of the Robotarium API are here. To download them, click the green code button, followed by Download Zip. After the files have downloaded successfully, navigate to your Downloads directory and extract the contents of the Robotarium MATLAB Simulator Master Zip file. You can move the extracted directory or files anywhere on your computer, but in this tutorial we will leave them in the Downloads directory. Now that we have the required software downloaded, let's boot up MATLAB to run our first example file and make sure everything works. Navigate to the directory where you saved the Robotarium MATLAB simulator files. The first step in running a simulation is to run the init file. This is only required once when you start MATLAB. If you do not do this and try to run a simulation, you will get some sort of error associated with a Robotarium specific function. Now, let's run the init file and navigate to the examples directory. This directory contains many examples that can help you develop on the Robotarium. For now, let's navigate to the plotting directory and run go-to-pose-with-plotting.m. If a simulation window pops up, like shown here, everything has been downloaded correctly and we're ready to write our first algorithm. With all the necessary software downloaded on our machine and working properly, let's develop our first few experiments, run them in simulation to see if they would work, and submit them to the Robotarium to get back any data that we would like to validate whether these experiments are actually working. With everything set up and running, let's go through our first example script and submit it to the Robotarium. First, create a directory to save our custom examples. This should be outside of the Robotarium MATLAB Simulator master directory. I've already made one named My Robotarium Examples and put some example scripts that we will go through. Note that you can really name this directory anything. There's nothing special about My Robotarium Examples. These files that I'm going to go through here are available through a link in the description of this video, so you can download them and follow along with me rather than writing them in real time. Let's first look at one robot circle example. The point of this experiment is to drive a single robot in a circle on the Robotarium. What we're going through this for is to familiarize ourselves with some of the Robotarium routines, as well as the velocity inputs that we give to our robots in order to move them effectively. Starting at line 5, I'm simply declaring a variable for the number of robots I'll be using in this simulation, which is going to be 1. Next, on line 6, I'm declaring the initial position of this robot, where I'd like it to start every time I run this experiment. For one robot, this is only a vector with 3 components: the initial x position, which I have at half a meter, the initial y position, which I have at 0 meters, and the initial orientation or heading that I want it to face. And this is going to be 90 degrees. Note that I multiply this by pi over 180 to convert it to radians. Every angle will be interpreted as a radian on the Robotarium, so make sure you don't put degrees by mistake. I'd also like to point out that the workspace of the Robotarium is 3 meters by 2 meters, with the origin of the testbed being the center of it. So the minimum x initial position is minus 1.5 meters, the maximum x initial position is 1.5 meters, the minimum y initial position is minus 1 meter, and the maximum y initial position is 1 meter. Next, on line 7, I'm creating an instance of the Robotarium class and saving it to the variable r, so we can call some of the Robotarium routines later more easily. To initialize the Robotarium class, the only argument that is needed is the number of robots you will be using in this experiment, like I'm declaring here. Some other optional arguments which I've included are a show figure argument, which will determine whether or not a simulation window will pop up when we run this experiment. Next is an initial conditions argument. This is whether or not we want the robot or robots to start in the same initial configuration that I've defined previously. If I didn't include this argument, the robots would be initialized randomly somewhere within the testbed. I don't want to do this when driving a circle though, because if I'm randomly initialized near the boundary and my robot drives outside of it, there's a good chance that my experiment will be rejected when I submit it to run on the actual Robotarium. Next, on lines 9 and 10, I'm declaring static, linear, and angular velocity. These are our unicycle commands with which we can control the velocities of the robots. So I'm setting a linear velocity to 0.1 meter per second, or 10 centimeters per second, and a static angular velocity to pi over 12 radians per second. These are the static velocities that I would like my robot to follow. Note that you can set these to anything that you would like in simulation. If I wanted, I could request my robot to move at 100 meters per second, and the cartoon on the screen or the simulation will probably move at around 100 meters per second. Unfortunately, when you submit this to the real Robotarium, this isn't the case. The motors on the robots have a limited range. They can't go 100 meters per second. They also can't go at about 1 millimeter per second. So you can't go really fast or really slow. The true range of the robots is somewhere between 3 centimeters per second to 20 centimeters per second, where you'll get reliable actuation. Next, we're going to use a Robotarium command called setVelocities, where we stage the velocity commands to be set to the robots. I have to give a first argument of the robot ID. I only have one robot, and the first ID that we're going to give it is 1, and the velocity command that I would like it to follow when I send it, which is going to be our unicycle command of v and omega that I set previously. Next, I'm creating a variable that's going to be a pseudo time variable. This is how I'm going to actually make my experiment run for a set amount of time. I've set iterations to 1,000 here in order to make it drive in a circle for 1,000 iterations in a for loop. The actual time that this is going to produce on the Robotarium is approximately the number of iterations times 0.033 seconds, or about 33 seconds total. We'll explain where this 0.033 seconds comes from in a second. Next, I'm going to have my for loop below. So for I equals 1 to iterations, so for 1,000 loops, I'm going to first get the poses of all my robots. This is required to be called before you iterate the simulation or send any velocity commands in order for the Robotarium safety routines to run properly if you submit this to the actual testbed. So if you call r.getStep, which increments the simulation, before you call r.getPoses, the simulator will error, and if you were to submit it, it would be rejected from the Robotarium. r.getPoses is going to query the position of all the robots in the simulation, or query the Vicon system, our motion capture tracking system on the Robotarium, to get the position of all the robots on the testbed. This 0.033 seconds that I talked about previously is because of the time delay it takes on the real Robotarium to actually grab this data. Next, I'm going to just step, and since I'm not creating any new velocity commands, this is just going to send the staged velocity commands to the robots on the real Robotarium or increment the simulation on your computer. Finally, at the very end, I'm using another Robotarium command called r.debug in order to print out any errors that might cause our experiment to fail or get rejected from the Robotarium. This looks good. Let's hit the run button and see what happens. As you see, our simulation window pops up. This black boundary is the workspace that would be on the Robotarium. So if your robot left this, it would be an error. And this little cartoon here is our robot, which drove in a circle, just as we expected. This didn't take 33 seconds though, because my computer went through it as fast as it possibly could. However, by using r.debug, we can get an estimate for how long our simulation would take if we were to apply it to the Robotarium. Down here, we have our simulation took approximately 33 real seconds. And then we have some error counts outputs. The first output is the time steps where the Robotariums were too close to each other. This means that there might have been a collision in the simulation that would cause it to be rejected if you submit it to the Robotarium. We only had one robot, so there's no chance we have two robots colliding with each other. We had 0 time steps where robots were outside of the boundary of the simulation. This is just, we don't want robots running off the testbed. If this were to happen and you were to submit it to the Robotarium, there's a chance that it could be rejected on those grounds as well. And finally is more of a warning, but it tells us that there are 0 stage velocity commands that exceeded actuator limits. This simply is trying to remind you that the motors can't move as fast as you want, nor as slow as you want. So if any stage velocity command exceeds the motor limitations, this will come up with the amount of times that happens and give you essentially a warning that the simulation you see will not reflect reality if you were to submit it on the Robotarium. Just to see this in action, let's actually change our linear velocity here to 100 meters per second and run it. As you can see, our robot took off like a rocket ship straight up. There was no circle here because our robot's moving really, really quickly forward. If we look down here at our errors, we have 848 time steps where the robot was outside the boundary. So that's an error that would cause us to be rejected from the Robotarium. And we had 1 stage velocity command that exceeded our actuator limits. That would be this one, or more technically correct, this stage velocity command that took this 100 meter per second velocity. Let's change our simulation parameters back to the way they were, save this, and submit it to the Robotarium so we can go through the process of seeing how we upload this simulation, compare the difference between simulation and reality, and see how we get back any data. To upload the script we just went through to the Robotarium, let's first navigate to the Robotarium website and sign in. This should bring us to our dashboard, which is painfully empty, but let's change that. First, let's click on the Submit New Experiment button. This will bring us to a page with a few things we have to fill out before actually uploading the script that we would like to run on the Robotarium. First, we need to give our experiment a title. We're going to call this Drive in a Circle. We need to give an estimated duration on how long our experiment is expected to last. The simulation printed out it should take about 33 seconds. So let's give ourselves a little cushion and say it'll take about 60 seconds to complete this experiment, just in case anything weird happens. Next, we need to provide an experiment description. This is for the Robotarium team to know what the platform is being used for. So let's briefly write down what we're using it for and why. This experiment should have 1 robot drive in a circle. This is an example script from the Networked Robotics online video series. Perfect. Next, we need to provide the number of robots that will be used during this experiment. Currently, you're allowed to use up to 20 robots, but in our experiment, we're only using 1. Finally, let's find the actual file that we would like to upload. We went through the 1 robot circle example, so let's upload that. Wait for this bar to become green, and then click it as a main file. If you had supplementary files, you would want to upload them as well, but make sure that the main file is selected so the Robotarium knows which file to run and which ones are supplementary to it. Finally, we hit Submit Experiment. And it's away. Just as we discussed in the development cycle, we're done. We're now going to wait because this experiment is in a first come, first served queue and will be pulled and run when it's our turn to run. After our experiment has been pulled and run by the Robotarium, we should receive an email notification that looks something like this to the email address that we signed up to the Robotarium through. Our experiment has been completed successfully, so the email tells us so. If it had not been completed successfully, it would tell us so, but in either case, we should view the results from our dashboard. Let's do that. If we return to our dashboard, you'll notice that our pending experiments are now empty. This is because all our experiments have been run. Down here in completed experiments, you'll see a few more than just the drive in a circle that I've submitted. We'll talk about these in a little bit. But for now, let's click on drive in a circle and look at the results that are returned to us from the Robotarium. This should look a lot like what we submitted to have our experiment run. It gives us a little bit of information about our experiment, when it was created, when it was last updated, its completion, along with our estimated duration and the number of robots. If we want, we can view or download the file that we submitted to the Robotarium, and there's a log output down here that if we look at, is just the command line output from the MATLAB container that we are running in. We're not interested in any of this though. What we really want to see is how did our experiment perform through an overhead video. So now if I click the video, it'll take us to an OwnCloud hosting server where we get to watch the experiment in real time. The first few seconds are the robots coming off the charging station onto the test bed, and then they'll execute our experiment. For time's sake, let's skip ahead a little bit, because it's a little boring watching our robot come out. After the initialization routine is completed, the first step that's going to happen is our robot driving to the initial position that we declared initially in our script. Remember, this is about half a meter over, facing 90 degrees, so straight forward. Then, our robot's going to drive in a circle. This looks pretty good and fairly similar to what we see in simulation. If you'll notice in the beginning, our robot jerked a little bit. This is due to motor dynamics that are not accounted for in the simulation. But this looks fairly good and fairly close to what we see in simulation. If we wanted to save this video, we can click the download button, which will download this video to our personal computer. And that's it for our drive in the circle example. But we're here to do multi-agent and networked robotics. So let's now look into examples that involve more than one robot. Before diving into the multi-vehicle case and seeing how we can actually control multiple robots simultaneously on the Robotarium, let's review some of the theory that we've gone over so far. Specifically, we're going to do a lot of planning in the single integrator domain during this video series. Meaning, we're going to assume our robot can move in any direction instantaneously. So we'll say, robot, I'd like you to drive in this direction. Unfortunately, as we talked about previously on the Robotarium, you can't tell a robot to just drive in this direction. You need to provide it with a unicycle command. You need to say, robot, I'd like you to drive this fast linearly, and turn this fast angularly. We give it a unicycle command. And so how do we rectify that? Well, we've covered it before, but let's go over it briefly again to remind ourselves. When we were covering the consensus equation, one of the first things we came across was, well, how do we make a robot drive to a goal position? And we thought one of the best ways to do this was to use a proportional controller, shown here, where we have our control input, u of I, is going to equal some scaling constant gamma, that's a positive number, times the difference between our goal location, where we would like to go, and our current location, x of I, where we currently are. And this is going to be a single integrator command, meaning it's going to produce a vector that points in a certain direction, like shown in this figure down here. Note that our robot really can't drive instantaneously this way, because we have to only move straight forward or turn, so we'd have to do some combination of the two. We call this a constraint. So our robot, just like a car or a bicycle, has wheels, and we cannot move against the wheels. So if you were parallel parking your car or parallel parking your bike, you can't instantaneously move sideways into the slot that you'd like to. So the robots are not points like we assumed with our single integrator dynamics. They have motion constraints, which we represent by the unicycle model here, where our control inputs are v, the linear velocity, and omega, our angular velocity. Luckily, in a previous video, we covered a near-identity diffeomorphism, or a fancy way of saying we can transform the single integrator dynamics, the nice easy way to plan in, to unicycle dynamics, which are more accurate to the way our differential drive robots on the Robotarium will actually move. So our planning structure throughout this video series, and in general when using differential drive robotics, is we will start off with the single integrator model. We will assume our robot can move in any direction. And while this is wrong, it makes planning much easier and is achievable by a differential drive robot. With our single integrator model, we will plan how our robots will move using our proportional controller. Once our proportional controller produces a unicycle velocity command we would like to follow, we're going to use our near identity diffeomorphism, or our single integrator to unicycle transformation, where we take our single integrator command, multiply it by these two matrices, which will produce a unicycle command, a linear velocity and an angular velocity, which we can feed to our robot to have it follow these single integrator commands as best as it can. This will be able to be approximated by our unicycle model, and this is what we can actually apply to the Robotarium. So with that brief review of the theory that we've covered so far, let's jump back into MATLAB, back into the Robotarium, and see how this can be applied in a relatively simple way using Robotarium routines that are pre-built for us. I've returned to MATLAB to go through an example script that will drive 3 robots to desired locations within the testbed. This will introduce additional useful Robotarium functions and consider practicalities like not having robots slam into each other. Let's open the multiple robot to point example script. This script is going to initialize 3 robots on the edge of a half-meter radius circle and simultaneously drive them to the opposite side of that circle. This is a nightmare scenario because we're basically developing a head-on collision, but we'll deal with that later. First, on line 5, I've set the number of robots we're going to use to 3. Like in the one robot circle script, I've also created the initial positions that I'd like for the robots to begin with here on line 9. With 3 robots, this initial position variable is no longer a vector, but a matrix of dimension 3 by the number of robots. In our case, we're using 3 robots, so this is a 3 by 3 matrix. The first row of this matrix is the initial x position I'd like my robots to begin in. The second row of this matrix is the initial y position I'd like my robots to begin with. And the third row of this matrix is the initial orientation I'd like my robots to begin in. Remember, this has to be in radians, and these angles are chosen such that the robots are facing inwards towards the center of the circle. Next, on line 10, I've also created a matrix defining the final positions I'd like each robot to reach in a very similar manner. The first row is the final x positions I'd like them to reach, the second row is the y positions I'd like them to reach, and the third row is the orientation. Note in this example, the final orientation will not be used. Next, I create the Robotarium object on line 13, using the same argument structure we discussed in the one robot circle example script. In order to drive our robots from one location to another, I'm going to use the single integrator dynamics we discussed in previous episode and a proportional controller to create the desired velocities that will drive the robots from initial positions to final positions. Line 16 declares the proportional gain for our controller, but recall that robots on the Robotarium are controlled through unicycle velocity command inputs, linear and angular velocity command, not single integrator. So line 21 is going to bring in a pre-made transformation function that uses the near identity diffeomorphism that was discussed previously to transform the single integrator inputs we will use to plan into unicycle inputs the robots can actually follow. Line 24 brings in barrier certificate functions. These are used for collision avoidance on the Robotarium. This collision avoidance algorithm is complicated and thus will not be covered in depth. But what it does, to give you an intuitive idea, is create the closest single integrator velocity input to the one that you have chosen that will keep all of the robots from colliding with each other as well as within the testbed. So it's guaranteed to keep those velocities safe. Now let's go through the algorithmic part of the code. We're first going to get the positions of all our robots in order to do the logic check for the while loop starting in line 30. This is just checking to see if all of the robots are within 5 centimeters of their desired final position. An important practical note here is declaring an error from our desired final position to be good enough. In simulation, robots will be able to drive to the exact final positions declared here. But this is not possible on real robots due to tracking error, motor dynamics. Remember that they can only move only so fast and only so slow. And there are other factors to consider that will not be discussed here. Thus, it's always a good idea to include these close enough statements when checking if a robot or multiple robots have achieved a desired state before you continue with your custom algorithms. In the while loop, we will update all the robots' positions, create new single integrator velocities we would like our robots to follow in order to drive them to the new desired locations on the other side of the circle, apply the barrier certificates to these newly created velocities to keep them safe, transform our safe single integrator velocity commands to unicycle commands the robots can follow, stage the unicycle velocities to be sent to the robots, and finally, send them with the r.step command. But let's briefly talk about the two new crucial Robotarium functions here. In line 33, the barrier certificate function takes in the created single integrator velocities for all of the robots, as well as the positions for all of the robots on the test bed. And this function creates a new single integrator velocity matrix, which we're overriding our old single integrator velocity commands in order to have our safe commands stored in the same variable that we were using to create previously. Next, on line 35, the single integrator to unit cycle dynamics transformation takes in single integrator velocities, the safe ones that we just created, as well as the poses of all of the robots, in order to transform them into unicycle velocity commands that our robots can actually follow, which we are saving in a variable dxu. For now, let's see what happens if we don't include the barrier certificate functions and submit a dangerous experiment to the Robotarium. So I'm going to comment out line 33 here, and let's run this example. As you can see, we get the warnings about our experiment in the debug output. We have 186 time steps where the robots were too close. And we can clearly see from the figure visualization that the robots passed through one another. Let's ignore these warnings and submit the script to the Robotarium anyway and see what happens. After submitting this erroneous experiment to the Robotarium in a similar way that we did with the one robot driving in a circle experiment, I've received back this notification after the experiment was pulled to run. It tells me that an error was detected in my submission and that I should see the error report.txt for more information. So, as we did previously, let's go to our Robotarium dashboard and look for the experiment that failed. I've named it Drive Multiple Robots to a Point, Failure, because I knew this was going to be rejected. Let's click on this to look at the information about this experiment. You'll see that there's no experiment video displayed here. This is because the experiment didn't run, so there's no video to be returned to us. You'll see there's a verifier log.txt. This is just the console output like you would see in your MATLAB script, but it told us to look at the error report.txt. So let's click the view button to see what it says. It tells us that robots were too close for 47 iterations. This makes sense. We knew this was going to happen, and the fact of the matter is that we've submitted an experiment that was going to cause robots to collide. The good news is we know how to fix this. So let's go back to see the simulation run with barrier certificates included and submit that to the Robotarium to see what happens when we include this barrier certificate function in real robots. I've come back to MATLAB to look at the multiple robots to point experiment again, but now with barrier certificates involved. Recall last time that we ran this, that the simulation had 186 time steps where the robots were too close. So now I'm going to scroll down and just uncomment the line where we're going to take our single integrator inputs and pass them through this barrier certificate function, which should make them safe. With this included, let's run this experiment and see what happens in simulation. The robots again charge towards each other, but you see that the barrier certificates make them do a cycle around each other in order to successfully reach the other side of the circle that we've defined. With the debug output, we see the simulation takes slightly longer. This makes sense because our robots now have to take time to get past each other, and that we have 0 time steps where robots were too close. We have a small warning here that there are 10 stage velocity commands that exceed actuator limits, but this is really okay because this is 0.3 seconds where the actuator limits are exceeded. So let's try to submit this to the Robotarium and see what happens. After submitting my experiment to the Robotarium, I've received another notification that it's been successfully completed this time. So let's go to our dashboard, as usual, and look at the results of this experiment. So I've drive multiple robots to a point, the success one. This is the one including the barrier certificates. Let's look at this. We can click on our example video to watch it. And again, beginning is going to be a little dull as we're going to watch 3 robots come out onto the testbed and initialize somewhere randomly within the testbed. So let's skip ahead. Our robots are going to first initialize to the outside of our half-meter radius circle, orient themselves towards the center, and then we're going to drive them into a collision. However, we've used the barrier certificates, which are going to keep our robots safe. So as you can see, as the robots are coming through, they make the necessary modification to their velocities in order to successfully reach the other side of the circle. We've now covered the basics of using the Robotarium, how to interface with the simulation API, submit experiments to the Robotarium, and receive back data from the Robotarium in order to see if your simulated experiments match reality. One thing I'd like to point out briefly is within the Robotarium MATLAB Simulator Master Directory is an examples folder. And within this folder, we have a lot of example scripts that will help you with your custom experiments that you may develop down the line. For example, in the barrier certificates directory, we have SI barriers. This is extremely similar to what we just went over with the multi-robots to point, where we have robots set up on a circle, drive through the center to the other side to demonstrate how the barrier certificates create collision avoidance. We also have plotting routines. This can be very handy in enhancing the visualization of your experiments. So, to give a network control example, we have leader-follower with plotting. This is going to have a single leader robot drive through 4 waypoints while maintaining a connected triangle formation behind it with 3 follower robots. If I run this, you see our leader robot is connected to the follower robots through this one connection of follower robot 1. You can tell who the leader is because it has a title above its head and each follower has a title above its head. We see the network topology displayed here, as well as the goal points G1 through G4 that our leader robot is trying to drive through. And just these little additions of plotting can really enhance your explanation when trying to tell others what your experiment is doing. And again, the backgrounds plotted here will be pushed to the actual Robotarium and plotted on the test bed. A very important note is you should go through these examples before you actually try plotting on the Robotarium, as there are tips and tricks that help optimize the plotting routines so that you aren't bogged down in computation when submitting to the real Robotarium, which can make your visualizations not look as good. And that concludes our introduction to the Robotarium. I hope that this video has given you a solid foundation on the Robotarium, what it is, what its mission is, and most importantly, how to interface with it, so much so that you feel confident in deploying your own experiments. Recall that this testbed was not made just for this network robotics video series. It's meant to quickly take someone's idea or algorithm and put it into an experimental setting where they can validate whether or not their experiment could work in reality. So if you have a crazy idea, feel free to throw it to the Robotarium. There you have nothing to lose. We have users from all over. We have biologists, social scientists, Girl Scouts, Boy Scouts, high schoolers. If you're trying to further your education or perform some sort of research, give it a shot. If you have any questions, concerns, comments associated with the Robotarium, feel free to reach out to myself or anyone else associated with the Robotarium project. We'll see you in the next video.